This is the sixth and final tutorial video in the Chemistry Key Skills series. In this video, we'll be looking over the empirical formula. In this tutorial video, we will look at how to calculate the empirical formula as well as the molecular formula for a range of compounds. We will look at how to calculate the empirical formula by experimentation, and we will balance equations using reacting masses. Our big question today is to explain how to find the empirical formula of magnesium oxide by experimentation. So far in this tutorial series, we have looked at molecular formulas. However, we can also calculate empirical formulas. These are the simplest ratio of atoms within a compound. Therefore, we need to have the smallest whole number ratio. For example, we could be given the molecular formula of glucose, that is C6H12O6. The numbers in the molecular formula of glucose are 6, 12 and 6. To simplify this, we divide each of these by the largest whole number that goes into all of them. The largest whole number that divides into both 6 and 12 is 6. Therefore, we have 6 divided by 6 for carbon, giving us 1, 12 divided by 6 for hydrogen, giving us 2, and 6 divided by 6 for oxygen, giving us 1. This gives us the empirical formula of CH2O. We can also use empirical formula along with the relative formula mass to work out the molecular formula. For example, the empirical formula of a compound is CH2 and its MR is 42. Our first step is to work out the MR of the empirical formula. We do this by adding up the atomic masses of the elements in the formula. So we have carbon and we have 2 hydrogens. Carbon is 12, each hydrogen is 1, giving us an MR of 14. Next, we divide the MR of the compound by the MR of the empirical formula. So in our case, we're going to do 42 divided by 14, which equals 3. Finally, to calculate our molecular formula, we need to multiply the numbers in our empirical formula by the number that we got in step 2. So we're going to do 1 times 3, which will give us C3, and then 2 times 3, which will equal 6. This gives us a final molecular formula of C3H6. Being able to calculate the molecular formula from the empirical formula is important, as the empirical formula of CH2 could refer to a variety of compounds. For example, C2H4, C3H6, which we have here, C4H8, and so on. We can also calculate our empirical formula from masses, so the masses of each compound that we know are involved. So for example, we may have a question where 3.2 grams of sulfur react with oxygen to produce 6.4 grams of sulfur oxide. What is the formula of the oxide? We've been given a few different pieces of information there. We've been told the elements involved, so we have sulfur and we have oxygen, and we've been given the mass of one of them and the overall mass of the product. In order to work out our formula, we need to do a series of steps. First of all, we're going to write down the element symbols. So sulfur is S and oxygen is O. Our second step is to write down the masses. In the question, we were given our mass of sulfur. This is 3.2 grams. We were not given the mass of oxygen. However, we were given the mass of the compound that they form. So they made 6.4 grams overall. 3.2 grams of this was sulfur. To work out our oxygen, we will do 6.4, take away 3.2, giving us 3.2 grams of oxygen. Our next step is to write down the AR values. These are their atomic masses from the periodic table. For sulfur, this is 32. For oxygen, this is 16. In step 4, we are going to divide the masses by the AR. So we will do 3.2 divided by 32, giving us 0.1 for sulfur, and 3.2 divided by 16, giving us 0.2 for oxygen. We now divide both of these by the smallest number. The smallest number was 0.1. So for sulfur, we do 0.1 divided by 0.1, which equals 1, and for oxygen, 0.2 divided by 0.1, which equals 2. Finally, we can now work out the formula using the numbers from part 5. We have 1 sulfur and 2 oxygens, giving us an overall formula of SO2. This can be expanded out to having 3 different elements present. In this case, it is exactly the same method. We can also use experiments to find out the empirical formula. The most popular one is to find the empirical formula of magnesium oxide. This uses the apparatus that is shown here. So we have our crucible and lid with our magnesium inside, and underneath we have our Bunsen with our tripod and our heatproof mat. We start off by measuring the mass of the empty crucible and its lid. This tells us the initial mass. We then put in a piece of magnesium and we weigh it again. This allows us to work out the overall mass of that piece of magnesium. We then heat it in the crucible above the Bunsen, lifting the lid occasionally to let in more oxygen. This will make sure that the reaction goes to completion. When the reaction is completed, we then allow it to cool and we reweigh the crucible once more. This will tell us the overall mass of the magnesium oxide. By taking the mass of the magnesium away from the magnesium oxide, we can calculate the mass of the oxygen that has been reacted. We can then use this experimental data to calculate the empirical formula of magnesium oxide. So for example, we heat 2.16 grams of magnesium. This was heated in a crucible, forming 3.6 grams of magnesium oxide. Calculate the empirical formula of magnesium oxide. Our first step is to calculate the amount of oxygen. In this case, we will do 3.6, take away 2.16, giving us 1.44 grams. Our next step is to calculate our number of moles. Thinking back to the previous tutorial video, we will do this by doing moles equals mass divided by mR. For magnesium, we need to do 2.16 divided by its mR, which is 24. This gives us a moles value of 0.09. And for oxygen, we do 1.44 divided by its mR, which is 16. This also gives us 0.09 moles. We then work out the lowest number of moles. This is 0.09, and divide both by this. This gives us a ratio of 1 to 1. This gives us an empirical formula for magnesium oxide of MgO, as we have a ratio of 1 to 1. In most chemical reactions, there is a limiting reactant. This is a reactant that will be used up. Once this reactant is all used up, it can no longer react, therefore the reaction stops, making it a limiting reactant. The other reactant will therefore be in excess, as there may well be some of it left over when the reaction has completed. This means that the amount of product formed is directly proportional to the amount of the limiting reactant used. The more limiting reactant, the more product, and the less product formed, the less limiting reactant present. We can also use a balanced chemical equation to work out the mass of the product formed from a given mass of the limiting reactant. First of all, we need to write out a balanced equation. We will then work out the relative formula mass of the reactants and products that we're interested in, calculate the moles for the substance that we know the mass of. Step 4 is that we will use our balanced equation to work out how many moles there'll be of the other substance. and then finally use this number of moles to calculate the mass. We can use this method to either work out the mass of the limiting reactant or the mass of the product formed. For example, magnesium oxide is made by burning magnesium in oxygen. What mass of magnesium is needed to make 200 grams of magnesium oxide? Starting with our balanced equation, this is 2mg plus O2 goes to 2mgO. We then need to work out our relative formula masses. For Mg, this is 24. For magnesium oxide, this is 40. 24 plus 16. We then need to work out the moles of the substance with the known mass. In our question, this was magnesium oxide, which we've been given a mass of 200 grams. We will then work out our moles by doing mass divided by mR, so 200 divided by 40, which equals 5. From our balanced equation, we can see that 2 moles of magnesium oxide is made by 2 moles of magnesium. This gives us a ratio of 1 to 1. We have 5 moles of magnesium oxide, so therefore we must have had 5 moles of magnesium. Finally, we need to work out the mass of magnesium. We will take our moles of 5 and times them by our mR, so 5 times 24. This gives us a mass of magnesium of 120 grams. You can also balance equations using masses, providing we know the masses of the reactants and the products. This will allow us to work out a balanced symbol equation. To do this, we divide the mass of each substance by its relative formula mass to find out our number of moles. We then divide the number of each of those moles by the substance with the lowest number of moles, just as we have done previously. This allows us to work out a ratio. We can then, if needed, multiply this up in order to make sure we have whole numbers in our ratio, and finally we can write out a balanced symbol equation. In the exam, you may also be asked to work out the mass of one of the reactants or products. You will do this by taking away the other masses from the total. Using the masses in this way is a type of stoichiometry. So, for example, 27.3 grams of carbon reacts with 72.7 grams of oxygen. This makes an oxide with a relative formula mass of 44. We need to write a balanced equation for this reaction. So our first step is to work out our number of moles. So we'll do 27.3 divided by the relative atomic mass of carbon, which is 12. This gives us 2.27. For oxygen, we need to remember this goes around as a diatomic molecule, O2. This means that it would have a relative formula mass of 32, 16 times 2. We do 72.7 divided by 32, which gives us 2.27. And finally, for our oxide, we need to work out our total mass. 27.3 plus 72.7 is 100, so 100 divided by 44, which equals 2.27. We will now divide this by the smallest number. The smallest number is 2.27, giving us a ratio of 1 to 1 to 1. Using this to write our balanced symbol equation, we have carbon, which is 1, plus 1 O2 goes to 1 CO2. As this is a 1 to 1 to 1 ratio, this is a very simple balancing. However, if, for example, oxygen had equaled 4.54, then we would have 2 oxygens, as this would be a 1 to 2 to 1 ratio. This can be applied to any calculation. We can also use masses to work out our limiting reactants. To do this, we have 3 steps. First of all, we have to work out the number of moles that were reacted. We then divide by the smallest number of moles in order to work out our ratio. Then finally, we compare this ratio to the ratio in the balanced equation. Using these ratios, you will find that there is one reactant which is at a higher ratio. This is in excess, therefore the other reactant must be the limiting factor. For example, consider the following equation. 2ZNO plus C goes to CO2 plus 2Zn. This is the balanced equation for the reduction of zinc oxide by carbon into pure zinc, releasing carbon dioxide. If we have 16.2 grams of zinc oxide and 0.6 grams of carbon, we can work out which one is the limiting reactant. First of all, we need to calculate our number of moles. So for zinc oxide, we will do 16.2 divided by its MR, which is 81, giving us 0.2. Likewise, we will do the same for carbon, where we will do 0.6 divided by 12, giving us 0.05 moles. We now need to divide both of these by the smallest number to work out our ratio. So we will do 0.05 divided by 0.05, which is 1, and 0.2 divided by 0.05, which is 4. This gives us a ratio of 4 to 1. This is the ratio using the masses. We now need to compare this to the ratio in the balanced symbol equation. Here we can see we have 2 zinc oxide and 1 carbon, therefore a ratio of 2 to 1. As we can see, in the ratio from the masses, we have a much higher quantity of zinc oxide than we do of carbon. This means that the zinc oxide must be in excess, whereas the carbon is the limiting reactant. So in this tutorial video, we have looked at how to calculate the empirical formula and molecular formula of compounds. We've looked at how to calculate empirical formula experimentally, and we've balanced equations using reacting masses. Our big question today was to explain how to find the empirical formula of magnesium oxide by experimentation. I want you to have a go at this question now. So first of all, we will get our crucible and heat it to get rid of any impurities. We will then wait for it to cool before weighing it along with the lid to find out its mass. We will then add in our magnesium ribbon and re-weigh it again to calculate the mass, this time to work out the mass of the magnesium. We then heat it, putting the lid on and opening the lid every so often to allow oxygen in until all of the magnesium ribbon has reacted. We will know it's reacted when it is turned white into magnesium oxide. We then wait for it to cool before re-measuring the mass, again with the crucible, the lid and the contents. This gives us the mass of magnesium oxide. We can use the difference between these to work out the mass of oxygen before working out the number of moles of magnesium and oxygen. We can then work out the lowest whole number in order to work out a ratio before finalizing our empirical formula. This concludes not only this video tutorial, but also the video tutorial series for chemistry key skills.